Hello everyone and welcome back to the next video in our ORCAD X keyboard series. My name is Adam, and in this video we're going to be covering how to create the key matrix for all of the keys on our keyboard. Now what I have here is I've actually created an appendix so that we can talk about why we use a matrix and also how we can avoid certain issues that come up with using this type of matrix connectivity, specifically for avoiding a problem called ghosting. So let's take a look at this first example here. So when creating our matrix, what we're going to create is essentially a X by Y matrix of keys or key switches, where one side of the switch is connected to one of these columns and the other side of the switch is connected to one of these rows. The way that it works is if you have, for example, 3 rows and 3 columns, so that's 6 pins, you can fit 9 switches. Excuse me. And that just keeps going up, right? So if you have 4 columns, 4 rows, that's 8 pins that we need to use on our microcontroller, but that means we can have 16 different switches and read each of those individually. That's really good. Basically, if we have 20 pins on our microcontroller, let's say that we use a 10 rows by 10 columns matrix, that means we can have up to 100 switches in our matrix with only using 20 pins on our microcontroller. So it's really good for especially our keyboard application, where we're going to have, I think, over 100 keys that we need to connect. But if we look at our controller page again, we only have, however many this is. I think it's just a little over 20 pins to work with. All right, so looking at this appendix, this is how essentially our matrix is going to be put together. So we have our columns, which are going to be outputs coming from our microcontroller. And then we're going to have our rows, which is the inputs going into our microcontroller. So let's take an example where this switch 16, and I've drawn a rectangle here. Let's take an example where switch 16 is pressed, meaning that the connection from this pin to this pin is shorted. So if we apply copy this here really quick. If we apply a logic 1 to this column, then as we see, it would be 3.3 volts in this case, but as we see logic 1 on each of these switches, right? This switch is open, so nothing happens. This switch is open, so nothing happens. And this switch is closed. So essentially that signal 1 or true or on, whatever you want to call it, 3.3 volts, travels through this connector to this wire and then gets output on this row 1 input. Right? So if we press switch 16 and we only toggle the first column, then we will see that only row 1 will see an input value of 1. So you can think of it, essentially extrapolate from there, right? As we go through each column, so if we have these 9 keys as an example, we can first toggle on column 1, see which key is pressed, then column 0, see which key is pressed, column 1, see which key is pressed, and then column 2, and see which key is pressed. And then what we read on the rows will basically give us a triangulation of which exact key is pressed in each exact instance. All right, so it seems pretty simple, but there are some caveats. The first is in this example that I'm going to show you here. So let's imagine a situation where we have 3 keys pressed at the exact same time. And this is actually pretty normal for when you're using a keyboard, right? Let's say, for example, you want to do Control-Alt-Delete if you're using a Windows computer. That will bring up the task manager, especially if you're having some issues on your computer. It's really important to be able to press those keys together. So if we see that, these 3 keys, in this case, they're not Control and Delete, but bear with me in this example. These 3 keys are pressed down, right? And if we apply a logic 1 to column 0, so we see logic 1 on all of these nodes here, it will travel over to row 1, which will see a logic 1. It will travel over to row 0, which will see logic 1, row 1, which will also see a logic 1, and then row 2, which has a 0, in which the switch is not pressed, we'll see a logic 0, right? So when we toggle logic 1 to column 0, not a problem. Everything works as intended. If we move over and apply logic 1 to column 1, we will get the signal traveling through here and go through the switch, no problem, and go to row 0, and we get a logic 1. However, the other problem that we see here is that this signal will then travel through this key that is already pressed and also make it look like, also see that switch 53 is pressed, meaning that let me rephrase. Because switch 50 here is also pressed, right? This logic 1 will then travel upwards in the opposite direction through the switch, and then also apply a logic 1 to our row 1, right? So if we trace this down, it goes through switch 51 here, up through this switch, and then through this switch here, and essentially we'll see a logic 1 on our row 1 input. So because we're toggling column 1, what ends up happening is our keyboard will think that this switch 54, let's not use green, let's go ahead and use orange. It will think that switch 54 is turned on because it sees a logic 1 on row 1. And when column 1 and row 1 both have a 1, that means switch 54 is pressed. And that is called ghosting, right? So we have these 3 keys in our matrix turned on, but for some reason, our microcontroller will think that this key is turned on, which is not. So how do we solve that? Well, let's think of the root of the problem, which is that when we had this switch 50 turned on and switch 51, and our logic 1 traveled through this wire, it traveled through here in the opposite direction and then fed through into our row 1, right? So what we need to do is essentially not allow it to go through in the opposite direction through switch 50. There's actually a component in electronics that is very well known for only allowing signals to travel in one direction. And you might already be thinking of it, and that is a diode. So if I go to the bottom here, you'll notice that I added diodes to each of these switches. And again, a diode, a simple general purpose diode, is a very cheap component. So it's not like we're adding a ton of cost to our keyboard. But by doing this, when we apply a logic 1 to this column 1, it will go through this pin, through the diode in the correct direction, and then it will go into row 0. So we'll see a 1 here, and then it won't travel up through this switch, right? Because our diode would be in reverse polarity. You would get no current flowing through here. Therefore, this would still be a 0 on row 1. So again, I apologize for the very long-winded explanation, but this is basically how we're going to construct our matrix of keys for our keyboard. So, this is only a matrix of 3 by 3, and it can support 9 different keys. We are going to be creating a matrix that has, I believe, 6 rows, and let me just check here, 19 columns. So if we multiply that out really quick, let me grab my phone. 6 by 19. So that can support up to 114 different key switches. All right, let's go ahead and start creating our matrix and see what we get. All right, so let's go ahead and get started on creating the matrix for our keys. Now on this key page, the first thing that I'm going to do is actually, let's go back to our appendix and just copy these rows here. Let me box select and copy these columns so that we have a good starting point. And we're going to paste them onto this page. And let's go into my place components. We want to look for the switch that we're going to use for our keyboard. Now, again, as you probably heard in some of the previous videos, I'm not going to be going over specifically how to create each switch symbol or each component symbol, each component footprint, But I did want to focus in on this specific switch because we're using something called alternate symbols in order to fit all the different types of key switches that you'll have on your keyboard. So if you look at a keyboard, and let me just take everything off my keyboard here, we can see there's my keyboard. Might be glitching a little bit with how I have the camera set up, but if you look at your keyboard, you'll notice that not all the keys are of the same size, right? So we have some keys that are slightly wider, and if you're working with, a numpad on your keyboard, you might also have some keys that are actually vertical in size instead of horizontal. So what we need to do is actually make sure that our switch can either support multiple different footprints, or you would have to then create several different symbols that each have their own unique footprint. And you can really do it either way. However, what I did is I have this switch component here. And if I go into my models and click on this and click footprints, you'll notice that I actually have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 different footprints that are assigned to this single schematic symbol. Now the way that's done is you basically just select multiple footprints, no big deal, but you'll notice that the primary footprint, let me just go back to the model selector here. The primary footprint is always going to be the first footprint which you select. Then as you select and check more of these, you will then add them to the alternate footprint list. What that allows us to do is when we actually place the component on our layout in our PCB, they will always default to this, primary footprint. But then we can simply use our right-click command or in the properties and choose one of these alternate footprints, which in this case, they don't have any different number of pins. They're simply just a wider version of each of these switches, right? So the switch component itself is just going to have the left side of the switch, the right side of the switch, and then maybe some mechanical holes for stability. But the keycap itself might be a little wider, right? So for example, our spacebar is the widest key on the keyboard. So if I look at this 6.25U, I'll talk about that in a second. It has this wide area here already designated for the entire spacebar keycap. Now the question is, how do we actually get those dimensions? So I found this website, and I really recommend you take a look at it. And what it essentially does is it provides a comprehensive guide for beginners for the different keycap dimensions. So if we look here, the standard keycap size is called 1U, or 1 dimension unit, and it is 19.05 by 19.05 millimeters, right? And that's essentially a placeholder space for everything like the plate switch hole, the keycap size, all the different mounting holes and whatnot would fit in here as well. But in general, when you're spacing one aside from the other, it will be this 19.05 by 19.05 millimeters. And then if you keep going down and look at the different keyboard layouts, you will see that each key has a standard U size, right? So Control, Alt, the function keys, the number, and the letter keys, these are all 1U, right? So 1.05 by 1.05 millimeter. Now, if we look at something like the backspace or the enter key, these will be 1.5U to 2.25U. It's not always standard. You can pick one and then maybe have a custom keycap that will fit that exact dimension. Or if we look at the Control, Alt, function key, these are 1U. Caps lock, tab, delete, anywhere from 1U to 1.5U. And if you've used different keys in the past, different keyboards in the past, you're probably familiar, with the idea that some of these can be slightly different between keyboards. And then, make sure you choose which standard you are most used to using. And then, use the appropriate U size for your keyboard. And this is just a nice little example of, for example, a keyboard, and you can see the different keys, right? So the escape, 1, 2, QW, these are all your 1U. The backspace here, if we look here, backspace is 2U. So backspace should be the exact same size as two 1U keys side by side. And then there's a couple other examples, right? So your ISO keycap sizes, your JIS keycap sizes. And we're going to use this and extrapolate from here to create our keyboard. All right, so let me minimize this. Go back into ORCAD here, and let's place our first switch, which is going right there. Actually, instead of placing a switch, let's just copy it from my appendix here, along with that diode, which we already placed before. And this is going like so. And then we just need to wire up the column and the row. So we want to make sure that the row extends all the way through because we're going to have multiples of these keys. And then that the column also goes all the way down because we're going to have multiple rows connected to each column. You can also just copy these wires as well. All right, so we have our first key placed, right? We have the diode, which is going to prevent that current flowing in the opposite direction, then making it look like we have a ghosting problem. And on this specific switch, I also have a placeholder here for the keyboard key. And I also have a placeholder for the unit length that I'm planning on using when actually placing these switches in my layout. All right, so I'm going to go through and actually place all of these keys. We're going to speed up this video so that you guys can maybe see really quickly how I'm doing this, or you can simply just skip ahead to the next section where we're going to talk about why I placed all of these the way that I did. And yeah, enjoy the sped up video, or see you in a couple seconds. All right, guys, so welcome back. Pretty much finished making the matrix here. So we have 2 pages, keys 1 and keys 2. We have rows 0 through 5 and columns 0 through 10. And then the columns continue through from columns 11 to column 18. Now you'll notice that there's some keys missing here. And that is because, well, if you look at your keyboard, for example, the spacebar, right, is quite a wide key. And there's not going to be any keys next to it because the spacebar is going to be taking up all of that space. So let's really quickly talk about why I set up these keys in this specific order. I have this other website here which I'm going to share, and any links that I use or any websites that I use in these videos you'll find the link to below. But if we go down here, you'll notice that there's something called the anatomy of a keyboard, which kind of talks about the function row, the numbers, your letter keys, and all of the different buttons like tab, caps lock, shift, control, alt, delete, etc. And if we scroll down here, there's something about the different keyboard sizes. So specifically, if you have a full-size keyboard, that means you have all the regular keys plus the numpad. There's what they call a 10 key less, which means it doesn't have the numpad on the right side. And then there's also this compact size, which doesn't even include things like the arrow keys. Now, for this specific example, for our video, we are going to be creating this full-size keyboard because if you go back and remember in one of the first videos, we talked about that we're going to be placing an LCD in this top right corner here, which will then also allow our numpad to act as a calculator and then use that LCD screen to display those numbers. So if you look at the full-size keyboard, I don't know if they have an example here, it doesn't look like it, but if you look at this image a little closer, right, so our top row would be everything from the escape to the F1 through 12, and then sometimes even things like print screen, scroll lock, pause, and then depending on your keyboard manufacturer, if you're using something out of the box, right, you might have some specific keys for like Bluetooth connectivity or, zooming in, dictation. There's a lot of other kind of custom keys that might be included. And if you are trying to create your own keyboard based on this video, you might even want to include some of your own custom keys. So think about what you would want on your keyboard, and really, as long as you change the function in the software, you can really include whatever you want. So again, looking at this as a reference, right, our row 0 here would start with escape. Our row 1 would start with the tilde and then go to 1, 2, 3, and so on. And then finally, our last column here would be like the numpad minus plus enter. And if we go into our keys number 2 page here, we see is numpad minus plus enter. Now we also want to organize this in a nice matrix and sort of line these up nicely too, vertically, because it'll make the wiring of all of these keys and switches on our PCB a lot easier. And you'll see that in, I don't know, maybe another 2 videos once we get to the actual PCB layout. But one last thing I wanted to talk about before we finish up with this video is that I've left the keys sizes or the unit lengths at 1U for now. And that is just because I don't exactly remember what the sizes are going to be. And if you remember in the first website that I shared, things like the tab key can vary, right? Sometimes they can be 1.25U, sometimes they can be 2U. If you look down at your own keyboard, right, your tab key might be about the same size as one of the letter keys, or it might be about twice the size of those letter keys. So your mileage may vary. And also if you're designing your own keyboard, you might want a larger tab key, for example. So really do whatever fits your own requirements. And I think that's it for this video, guys. In the next video, we will cover the rest of the, we got 2 more videos on the schematic specifically for the LEDs. And then we also have one for the LCD, which is where we're going to have that I2C IO expander. And then we're going to be hooking up our LCD to that IO expander as well. So 2 more schematic videos, and then we'll get started on the PCB layout, and hope to see you guys there. Again, thank you for watching. Questions or comments, please leave them below. And yeah, I'll see you guys in the next video. Thanks. Bye-bye.